component and model that. The S is the seasonal component, and we can do that through dummy variables for months and all that kind of good stuff. And that's pretty straightforward. The C is really the hard part. C is usually some underlying cyclical component that we can see but we can't account for. So just the economy, modeling GDP, for example, is we have this thing called a business cycle, and we got a name for it. But I guess if you asked 20 macroeconomists what the business cycle is, you'd get probably 20 different answers because we can't observe it. And if we can't observe it, we can't really model it. So there's no set of dummies we can include. There's no set of there's no variables we can add in there to account for something that we don't observe. And this is pretty common in the wine industry as well as in the grape industry. There's a paper I wrote years ago about modeling grape price cycles. And what you can do is you can see these underlying cycles in grape prices that are just about as just boom, boom, boom. But we don't know what explains it. We don't know if it's the weather. Is it these every 7-year El Nino things where you get these 7-year weather patterns, as well as the cyclical nature of the grape prices is different across regions and varietals. So this could be like Cab, where you'd see one that's a lot more subtle for Chardonnay, and then one that's counter-cyclical to this one for Mendocino versus Napa versus Sonoma versus whatever, and it's really difficult to model because we don't know what would cause it. So it could be some of this could be over planting. So the movie Sideways comes out, we see lots of planting of Pinot ripping out of Merlot grapes. And so you get a glut and prices fall, and then they rip those out and then prices rise. So it could be that, it could be, nobody knows, to be honest. So modeling it is really difficult. And if you can come up with the model, then that's good. And that's what that article is about. I don't know what happened to that article. So how do we do this? And epsilon is the error term, which we already know. So how do we, again, we know how to model the trend, we know how to model the seasonal component. The cyclical component is something that is difficult to do.
Oh God.
What we're going to use is something called an autoregressive moving average model.
So many words, it has an acronym. Also.
ARMA, yeah. Real common in, again, the forecasting. So the job that she was going for was supply chain forecasting, is that right? Or analytics, something like that? Mm-hmm. And supply chain is all about forecasting final demand and then kind of working backwards. At least that's the way it should be. Because you don't want to forecast intermediate steps, because in the end, it's the consumer that's going to drive kind of the inventories and all your inputs and all those things. So these ARMA models are pretty common in the whole forecasting literature. They teach entire classes on just this one topic. We're going to do it in one day. So don't worry about the notation. This is just the notation that goes along with the literature. So this is phi, and this is theta. And all this means is that these are going to be lagged y's, which are the dependent variable. Autoregressive, that's the autoregressive portion. These are going to be the lagged errors, which are the moving average portions. So the notation is nasty, but it's pretty simple. Okay, so y is our sales or whatever, grape prices or whatever it is we're trying to forecast. Remember, epsilon is supposed to be this purely random component of the model, stuff that we can't explain. But there shouldn't be any pattern to the error term. In the forecasting literature, they use the term white noise. White noise is the definition of white noise is an error term that has no pattern. It's just perfectly random. It should be perfectly random. And that's what we want. We want our error to be random so that we're not consistently overestimating or consistently underestimating stuff. So our goal is to have a white noise error term. But we know that with time series data, there are always going to be these serial components to the error term, and we need to be able to fix it. So again, white noise, the average error should be 0, the expected value is 0, the variance is sigma squared, and the correlation between any lag values should be 0. That's all that says. We want that. So we want white noise. And phi of L, and L is for lag. Phi again is our lag component for the autoregressive part, and theta of L is our lag component of the moving average part. So when we're including lag Y's, those are called autoregressive processes. When we're including lag error terms, those are the moving average processes. And we can have solely autoregressive processes, solely moving average processes, or we can combine the two. And the idea is to improve the prediction, reduce any persistence in the error term, which again results in improved forecasts. So forecasting, again, this is a big part of that. All right, so we already just said this. We just said that's the autoregressive portion, that's the moving average portion. All right, so here we go. Yeah, so the notation, let's just skip this, but the notation is such that here's our autoregressive portion. It's a 2-period lag, so this is, so if we multiply this through, this is the current Y, 1-period lag Y, and 2-period lag Y. So we're not going to be concerned with any of that stuff. It's going to burn through this stuff and get to a process. So here are 2 moving average processes. And what I did was I actually constructed these using a simulator. So there's this data simulator you can use in Stata, and it'll construct a moving average process with theta equal to 9. In this case, the theta equal to 4. And as you can see, so again, theta is, yeah, so our error term has a shock over 2 periods, the current period and the delayed period. And as you can see, they're pretty similar. So a theta pretty high of 0.9 compared to a moderate theta of 0.4 results in pretty similar processes. Kind of indicating that this persistence, this moving average structure, is a relatively, I guess I use the term short memory, but basically weak dynamics. There is some persistence, but it's not a real strong persistence. So it's not obvious like I had drawn before, right? Where you got these cycles that we can't explain. Here there's an underlying cycle, but it's a relatively weak cycle. All right, so here's how you write it out. And this is really all we care about. So theta is in the blue line, it's relatively high at 0.9, and then for the red line, it's relatively low at 0.4. Either way, we're talking about relatively weak dynamics. So we've got an underlying cycle, but it's going to be kind of subtle, something like that, where you really have to squeeze to look at it. The tricky part of these ARMA models is trying to identify whether it's a moving average process or whether it's an autoregressive process or if it's some combination of the two. And that's really the hard part of this. And it's as much art as it is science. We're going to use a lot of the same tools we used before. We're going to use information criteria. and some of the other things, autocorrelation, partial autocorrelations, and those things. So, but yeah, here's a moving average process. One way to identify a moving average process is through, let's ignore that. Let's ignore that. Yeah, is by examining the autocorrelation and partial autocorrelation functions. So, classic signs of a moving average process are abrupt cutoff of the autocorrelation function. So remember, anything within this 95% confidence interval, those the bands, whatever they're called, is not considered statistically significant. So classic sign of a moving average process is that these things collapse to zero, which anything in this is considered, relatively quickly. So the autocorrelation coefficient shows us, gives us a hint as to whether it's a moving average process or an autoregressive process, although we haven't looked at the autoregressive process yet. But this is kind of a classic indicator of a moving average process. For the for the partial autocorrelation coefficients, again, a distinctive feature is decay. So, and decay can be one of two types. It can be oscillating decay, which means it's big, it's getting smaller, but it's oscillating back and forth. Or it can be one-sided decay, and we'll see both cases. So this is pretty indicative of a moving average process. And the partial autocorrelation coefficient also gives us some insight into the order of the moving average process. Is it an MA1, MA2? In other words, how many times do we include a lagged error term in our regression? And that's what we want to try to figure out. Any questions?
So Alex is telling us how many lags we should use?
So here it's usually going to be the partial autocorrelation coefficient. So since only the first one is really statistically significant and these ones become significant but they're kind of past there, that's going to give us a clue as to whether it's a moving average 1 process or a moving average 2 process. And we'll look at a moving average 2 process to see if we can see that significance. But the main thing is autocorrelation coefficients, abrupt decay, and then abrupt collapse, I should say. And then for the partial autocorrelation coefficients, we're looking for decay of some sort, either oscillating decay or one-sided decay. And that gives us a clue as to whether theta is positive or negative. All right, so here's the moving average 1 with the theta of 0.4. So again, abrupt decay, oscillating, and you can see how our partial autocorrelation and partial autocorrelation are pretty close to the theta of 0.4. Here it's 0.9, and we're not really getting to the order of that. But that's fine also, because we don't need to specify that. The models, or that's going to be estimated in our regression. All right, so if we had seen these, we'd know to probably use, well, first thing we looked at the data and we said, okay, maybe there's some persistence in the data. We look at the autocorrelation and partial autocorrelation coefficients. We see that, yeah, these are all indicative of a moving average process. So perhaps we model it that way. All right. We got higher, it's just higher order processes. So here's one with, here's a moving average 2 process. And again, it's simulated, so I constructed this. With theta 1 equal to 0.9, theta 2 equal to 0.1. And let's see if we see kind of those distinctive features. Again, abrupt fall off of the autocorrelation coefficients, and we're not really getting a hint as to the second order nature of our moving average process. So we're not really seeing kind of this, and then this one being significant, and then these dying off. So again, these are helpful tools, but they're not foolproof. So in the end, we're going to probably play with different specifications. We'll change the order of the moving average coefficient, we'll add an auto-regressive portion, and so again, in the end, we're always trying to figure out what the heck's going on and find the best model. Okay, so let's talk about the autoregressive process. So here's an autoregressive process. I use the same values for the autoregressive process, but notice that an autoregressive process with a phi of 0.9 shows a lot more of this kind of persistence, really pronounced cyclical effects, as opposed to an autoregressive coefficient of 0.4. So there's still, I should include those separately, there's still some persistence or some cyclicality in the red autoregressive process, but it's not as prominent as that of the blue one. And again, remember, we don't know what's causing these cycles. These underlying cycles are just out there for some reason. Business cycles, weather cycles, planting, whatever it is. All right, so can we use, again, contrast this with the moving average process, which was real subtle. We couldn't tell the difference between any of those things. Autoregressive processes are able to capture much richer dynamics, much more pronounced cyclical events. All right. So let's skip through this and go to our that. Again, examining the autocorrelation coefficients and the partial autocorrelation coefficients. So for autoregressive processes, gradual decay is a sign of an autoregressive process as opposed to abrupt fall off. Phi should be greater than 0, which is relevant for us. Phi is small, then it decays rapidly. Phi is large, then it decays more slowly. For the partial autocorrelation coefficient, we should see abrupt cutoff after in this case, if it's an AR1 process, after the first partial autocorrelation coefficient. Again, if phi is less than 0, you're going to get these back and forth oscillations. Let's see. So here is the AR1 with the phi of 0.9. Again, unlike the moving average process, which we saw these abruptly fall, this is going to have that gradual decay. And again, in this case, we can see that, again, the partial autocorrelation coefficient gives us the nature of the process in that only that first one is significant. And then we see this kind of oscillating decay. But none of those are statistically significant anyways. So if it's a pure moving average process, it's pretty easily to identify. If it's a pure autoregressive process, it's pretty easy to identify because the nature of the autocorrelation coefficients and the partial autocorrelation coefficients are really different. Right? So it's pretty easy to identify, again, a pure AR and a pure MN. The problem becomes when you have both, you combine both of them, you have an ARMA process. All right, let's look at the, so, okay, 0. Yeah. Let's look look at the other one. I didn't do the 0.4 one? Yeah, let's not do that. Let's see, so here's an AR2 process with phi 1 of 0.9 and phi 2 of 0.4. Looks like negative 0.4, actually. And in this case, we have we don't have the gradual decay. We have kind of an abrupt decay, but we do see clear signs that it's an AR2 process, in that the first two partial autocorrelation coefficients are statistically significant, and then the rest kind of collapse to zero pretty quickly. So there is some geometric decay, but it's following, it's kind of here, and then it comes back here, and then it goes back up. So it's not oscillating back and forth. It is, I guess, decaying somewhat, and you can see that pattern there. So what you're looking for is a pattern. Either some sort of decay or some sort of abrupt cutoff. And again, for the partial autocorrelation coefficients, they become zero after the second lag. So again, this would give us hints as to we should probably be using an autoregressive process, a second order autoregressive process. Which just means that in our model, we would have sales, for example, beta 0 plus beta 1, and we would include sales, 1 period lag, plus beta 2, sales, t minus 2, plus our error term. So this is a AR2 process. That's what all that is. So operationally, this is how we would implement it. Although we're not going to use our reg function, because this has to be estimated using a different function. All right. Get a good shot of this, because this is, I still use this. This is again giving us a hint as into what we're looking for in our autocorrelation functions and our partial autocorrelation functions. Remember what I said, if it was a pure AR1, it's pretty easy. You see this geometric decay of the autocorrelation function and then sharp cutoff of the partial autocorrelation function. If it's a MA1, we know that, again, it's pretty distinct in its look. You get a sharp spike at that first lag, if it's MA1, and then oscillating decay or geometric decay of the partial autocorrelation coefficients. For higher order autoregressive processes, you're going to get some combination of geometric decay, either one-sided or damped oscillations, or a combination of the two. And for the partial autocorrelation coefficients, they should collapse towards zero after the pth order, which is the order of your autoregressive process. For higher order moving average processes, again, the autocorrelation coefficients should collapse towards zero after whatever the order is, first Q processes. The partial autocorrelation coefficients should die out, again, in a decaying fashion, which is exponentially, or in an oscillating fashion, or in some combination of the two. So some of that math stuff that we were looking at had to do with the nature of the roots of this, whether they're real or complex, and we don't need to get into all that stuff. Essentially, we can just look at the autocorrelation coefficients and the partial autocorrelation coefficients and try to figure out what the heck we're doing. Now, if we have both an autoregressive and a moving average process, then you gotta combine all these things. So if it's, for example, an AR11, so we have a autoregressive process of order 1 and a moving average component of order 1. Then we're gonna get geometric decay, which is nice, and for the autocorrelation coefficients, and then oscillating decay for the partial autocorrelation coefficients. Again, assuming phi is positive, which it's going to be in our cases. So a negative phi we won't come across a negative phi. If it's a higher order autoregressive moving average component, so this could be 2 and this could be 5 or some combination of that, then you're going to see either direct or oscillating decay after the first Q lags, where Q is the moving average component. And then you're going to see either direct or oscillating decay after the first P lags, where P is the autoregressive component. So again, we're trying to guess at what's the nature of these processes. And it's not necessarily real easy. Remember that the goal is to, if we have some underlying cycle that we can't model, then we're going to get a pattern in our residuals. And our goal is to eliminate those patterns, eliminate the serial correlation in our residuals, and increase the accuracy of our forecasts. So what we're going to do is have a test for white noisedness, which means we've eliminated any predictable elements of our errors. 2 simple tests, the Box-Pierce Q statistic and the Lejeune Box Q statistic. They're both pretty similar. The null hypothesis is that our errors are white noise, which is good. And the alternative process is that no, they're not white noise, which is bad. And we'll just pull a command, we'll get the command for that. The Lejeune Box Q statistic follows a chi-square distribution, and we'll get to that. So let's do, yeah. Let's see what the heck we're doing. All right, so let's go into, I want to do a simulation. All right, so you don't have this, but I do. So essentially, there's this simulation program. I'm going to construct those same 2 moving average processes. Well, let's do some methods. We'll just do it. So essentially what we do is we bake in serial correlation. So there's 2 series, let's call it Y and Y2. We know there's some persistence or serial correlation in there. The first one is a moving average process with theta of 0.9. The second one is a moving average process with theta of 0.4. We know there wasn't much difference between those 2 moving average processes. Moving average processes are used to model relatively weak dynamics like this, as opposed to much more rich dynamics. So step 1 is we kind of look at those 2 processes. So we graph our sales, right? And again, just like we showed in the PowerPoint, they're pretty close. They're real close. If you look at the blue line with theta of 0.9, you can see that the peaks are a little bit higher, the troughs are a little bit lower, but in the end, they're really, really close to each other. So again, moving average processes don't pick up. Plus, I mean, do you see much of underlying cyclical effect in there? We know it's there. We're 100% certain it's there because we constructed the data set to have a persistence in there, and we even specified the level of persistence. But again, it's one of those situations where you use a moving average process to model cyclicality that isn't real prominent. All right. So how do we do? We already showed you how to do the autocorrelations and the partial autocorrelations. And I like to combine these because we use them together. And again, abrupt cutoff is a distinguishing feature for a moving average process, and then decay of the partial autocorrelation coefficients. And same thing for 2. All right, so let's try to model that process. So I'm going to regress y on time. I'm going to predict the values, and I'm going to save the residuals. So remember the option R is to save the residuals. So let's see how good ordinary least squares is at modeling a moving average process. I don't know if you can see this, or if you can tell, but that's not a line at 0. That's the actual regression.
Got a little bit of it.
Yeah. The problem is there's no independent variables there. There's nothing there to tell it to move up or down. Remember, these are unexplainable. Just like we said with El Nino or whatever these other things are, it's completely unexplainable. So it's horrible. Let's say the residuals. Remember, the residual is the difference between the actual and the predicted, and we should see a pattern in the residuals. So this just tells us how bad ordinary least squares is in the presence of some underlying cycle that we have no idea the cause of. There's nothing we can do about it. Now, we're probably going to have some independent variables in there in our model, and we're probably going to have a little bit better prediction. But again, this is the case where we just don't know what's causing them. But we still need the model. Let's take a look at the residuals. And the residuals basically follow the same pattern as that process. So it's kind of hard to see. So let's look at the autocorrelation and partial autocorrelation of the residuals, the error terms themselves. And what we'll see is that it's kind of classic.